Evaluate definite integral of sine 2 theta respect to theta from 0 to pi over 4. So by the fundamental theorem of calculus, we can take the antiderivative first and then evaluate at pi over 4 and subtract the evaluated 0. So first we need to take the antiderivative of sine 2 theta. We know that if we take the derivative of cosine 2 theta, we get negative sine 2 theta times 2, right? So it has been negative. So that derivative of cosine 2 theta is negative sine 2 theta. So negative negative becomes positive sine 2 theta. We also need to divide by 2. Okay? And evaluate at pi over 4 and evaluate at 0. So let's check that work real quick before we evaluate. We know that if I take the derivative of negative sine 2 theta over 2, I get negative sine 2 theta over 2 times 2 by the chain rule. These cancel out, so I have sine 2 theta. Okay, so we just check that this antiderivative is correct. So in order to evaluate the definite integral by the fundamental calculus, what I do is I plug this number and subtract by when I plug this number. Okay. So let me do 2 parentheses. Negative cosine of 2 times pi over 4 over 2 minus plugging 0. Negative cosine 2 times 0 over 2. So I plug pi over 4 here, and I plug 0 here. And we just simplify to evaluate. We get here negative cosine pi over 2 over 2. Negative negative, so we can write plus cosine 0 over 2. Well, cosine pi over 2 is 0. So, and cosine 0 is 1. So what we have left is essentially 0 plus 1 over 2, which is 1 over 2. So 1 over 2 is the final answer, the definite integral of this problem. Let's evaluate this definite integral. First, we need to find the antiderivative, which is 2x squared over 2. Okay, it's not over 2. Actually, it is over 2, but then we can cancel 2 out. Plus x. Evaluate at 5 to 0. But actually, 2 and cancel out, so we have x squared plus x, evaluate 0 to 5. Right? So we can again check it. If I take the derivative of x squared, I get 2x. If I take the derivative of x, I get 1. So let's evaluate. So first, I plug x squared. I plug 5 here first. I plug 5 here. Let me actually write it. Just plug 5. So the first parenthesis, I plug 5. So 5 squared plus 5 minus, again I'm plugging 5 to the x, both variables, and minus plug 0 here and 0 here. So I'm highlighted this color as 0. So I get 0 squared plus 0, which gives us 25 plus 5 minus 0, which is 30. So this is our final answer. For this one, we need to remember the derivative of arctan. So we know that if I take the derivative of arctangent x, we get 1 over 1 plus x squared. So if I take the antiderivative of this, I get arc tangent x. But we're evaluating. This is definitely evaluating at these endpoints. So let me do this on the side. So then we plug this value and subtract from this value. So let's do that. Arc tangent of 1 minus arc tangent of 0. Okay, so 1's from here, 0's from this right here. Oops, sorry, different color. So then we know that arc tangent 1 is pi over 4, right? Tangent pi over 4 gives us 1. And arc tangent 0 is 0. So final answer is pi over 4. So for this definite integral, first we need to find the antiderivative first. So let's rewrite this as x to the negative 2 power. So we can apply the reversing the power rule. So then when we take the antiderivative, we get x minus 2 plus 1 x, divided by negative 2 plus 1. Since it's definite integral, we don't write plus c, we just do this. And this is x negative 1 over negative 1, right? Which is same thing as negative 1 over x to the 1 power. Okay. So then now we plug this value and subtract after we plug this value. So let's do that. We have negative 1 over 3 minus negative 1 over 1. Again, 3 is from, we plug the upper bound first and the lower bound, 1 right here. So what this gives us is negative 1 over 3 plus 1 over 1 is negative 1 over 3. This is 1. We need to common denominator, so I'm going to write 3 over 3, which gives us 2 over 3. So this is the final answer. So for this one, first we take the antiderivative. Well, we know that derivative of secant is secant x or secant theta tangent theta. So if you take the antiderivative of secant theta tangent theta, we get secant theta. Evaluate it at 0 and pi over 3. So first we plug this value, evaluate, and subtract, plug 0 in, value. So we get equals secant pi over 3 minus secant 0. So when we evaluate this, well, let me color here first. This is from here. When we evaluate this, well, secant is same as 1 over cosine. So we have 1 over cosine pi over 3 minus 1 over cosine 0. And cosine pi over 3 is 1/2. So we have 1 over 1/2 minus cosine 0 is 1, 1 over 1. 1 over half is 2 minus 1 equals 1. So this is our final answer. For this one, we need to take the antiderivative of tangent square y. But we don't know directly of a function that if we take the derivative, that we get tangent square y. But here we can use something else. From the Pythagorean identity, Pythagorean trig identity, we know that tangent square theta equals secant square theta minus 1. Therefore, instead of finding tangent square y, we can rewrite this as secant square y minus 1 respect to dy. Then we know the antiderivative of secant square y. So we can take the antiderivative, which is tangent y minus antiderivative 1 is just x. And we evaluate this at pi over 4 and 0. Right? So first plug pi over 4 to, oops, sorry. I meant to write y there. We're working with variable y. So first we plug pi over 4 to both of these variables, and then we plug 0 to both of the variables, right? So let's do that. We have tangent of pi over 4 minus pi over 4 minus tangent of 0 minus 0. Okay, so make sure you pay attention where these variables come from. So we do parentheses first. So we evaluate this first, and then we subtract from each other. Well, tangent pi over 4 is 1 minus pi over 4. Tangent 0 is 0. So we have 0 minus 0. So essentially we are left with 1 minus pi over 4. So this is our final answer. I mean, we could write it common denominator 4 minus pi over 4, but either one's fine. Okay. So for this one, what we had to do is using Pythagorean identity, we have to rewrite this tangent square as secant square minus 1. Because we know antiderivative of secant square x, or secant theta theta, in this case, secant square y. Let's take this different integral from -2 to 1. Sorry, -1 to 2, x squared minus 3x. So first, we want to take the antiderivative, which is x cubed over 3, reversing the power rule, minus 3x squared over 2 from -1 to 2. And again, you can always check if you take the derivative of each of these. If you take the derivative of this, you get x squared. If you take the derivative of this, you get 3x. So let's evaluate positive 2, and then evaluate a -1 and subtract from each other. Right? So first plug positive 2 minus 2 square over 2 again. So this first, and then we subtract. So let me do this first. We're plugging 2 and 2 here, and we subtract after we plug -1. So we're plugging -1 here and here. So let's simplify these. We have 8 over 3 minus, is that 12? Well, actually we should cancel one of them out. So we have 1, 2, so we have 6. Minus -1 over 3 minus 3 over 2. Okay. So let's simplify this one. 8 over 3 minus, we need to have a common denominator, so I'm going to write it as 18 over 3. Common denominator, we need to have a 6 as a common denominator here. So we have -2 over 6 minus 9 over 6. So let's say again, negative 10 over 3 minus negative 11 over 6. Oops. Then we need to have a common denominator again. So we have negative 20 over 6 plus 11 over 6 gives us negative 9 over 6, which is negative 3 over 2. So this is our final answer, definite integral of this. For this one, first we need to take the antiderivative by reversing the power rule, like this, and evaluate at 1 and 0, which is same as x to the 100th power over 100, 1 and 0. So when we evaluate this, first plug 1 and subtract plug 0. So 100th power to 100 minus 0 to the 100th over 100. So again, I'm plugging this one right here. Oops, sorry. Right here. And plugging this 0 right here. So let's simplify this. This is just 1 over 100. This is 0. So we have 1 over 100. So this is our final answer. So first, we need to come up with the antiderivative of this function. So let's talk about that. If we take the derivative of e to the 3x, we get e to the 3x times 3 by the chain rule. Therefore, if I take the derivative of e to the 3x divided by 3, I get e to the 3x over 3 by chain rule times 3. So cancels out e to the 3x. So that means antiderivative of this is this right here, e to the 3x over 3. So antiderivative of this is e to the 3x over 3, evaluated 0 and ln of 2. So let me do a part here. So at this point, plug this in, and subtract. And it has to be this order where we plug the upper one first. E to the 3 ln 2 over 3 minus e to the 3 times 0 over 3. So I plug ln 2 here, and I plug 0 here. And maybe it's good habit to always actually print this around it to show that we're plugging in 2 different times, at upper bound and lower bound. So let's simplify this a little bit. Here, for this 3, actually can go up right here. Right? So we have ln e to the ln of 2 to the 3 power over 3 minus e to the 0. This is essentially 0. Anything to 0 power is 1. So we have 1 over 3. And then e and ln are inverse function each other, so they cancel out. So the numerator simplifies to just 2 to the 3rd. And that's why we rewrite it that way. We wrote it that way. 1 over 3, which is 8 over 3 minus 1 over 3 is 7 over 3. So this is the answer for this problem. Final answer for this problem. Compute the derivative, or dy dx, of the function y equals 0 to x cosine negative 1, so cosine inverse a dA. So a is the variable here, well, for inside function. Remember, this entire thing is a function here. So what we're finding here is taking derivative of this function, this area function, respect to x of this 0 to x cosine inverse a dA. Okay, so this entire thing is an area function, right? And we're taking derivative of that respect to x. And by the fundamental theorem of calculus, this is just cosine inverse x. And that's it. Right? So it is important for us to see that this itself is an area function, specifically an area function, from 0 to whatever x is. So it starts at 0 and it finds the area between this curve and x-axis from 0 to x, the net change. Right? If we take the derivative of this function, we get cosine inverse of x. Compute the derivative of the function y equals integral from x to 5 of square root of 1 plus t squared dt. Here we have an area function. This entire thing is a function. Right? So we're taking derivative of that function. So we have area function x to 5 square root of 1 plus t squared respect to dt. And we're taking derivative of this function. So when we take the derivative of this area function, we can apply the fundamental theorem of calculus. But fundamental theorem of calculus tells us that we can only apply when we have numerical constant on the lower bound. So we can actually rewrite this by the integral property of integral. We can switch the lower and upper bound by putting negative sign. So 5 and x, we can switch the lower and upper bound if we put negative sign here. And inside stays the same. Then now we can apply the fundamental theorem of calculus here, taking derivative, which we just get negative, keep the negative sign, 1 plus x squared. So we took the derivative of that area function, and this is the derivative. Compute the derivative dy dx of the function y equals integral, definite integral from 0 to x squared of square root of 1 plus t squared dt. So here, this entire thing is a function, and we're taking derivative of that function. So we take the derivative of that function with respect to x, and the function is 0 to x squared square root of 1 plus t squared dt. We're not taking antiderivative, or we're not taking derivative integral here. This entire thing is a function, area function, specifically area from 0 to x squared under this curve, respect to t. Right? So we apply the fundamental theorem of calculus, where when we take the derivative of this thing, we get one plus, we plug this, we think is this becomes the variable for t. So we have actually x squared to the second power. And because this is not x, it's x squared, we have to apply the chain rule. So we have to multiply the derivative of x squared. So we get square root of 1 plus x to the fourth times 2x. Or we can rewrite it 2x times square root of 1 plus x to the fourth. So this is the final. So this is the derivative of this function right here. Compute the derivative dy dx of the function y equals integral from 0 to cosine x of square root of 1 plus t squared dt. So here, this entire thing is a function, area function. We're taking derivative of that function. So take the derivative of the function, the area function. What is that function? That function is just integral from, definite integral from 0 to cosine x of 1 plus t squared dt. And by the fundamental theorem of calculus, when we take the derivative of this, we're taking derivative. The t is just cosine x now. So we have 1 plus cosine square x, this is square. But because this is cosine x, not just x, we have to apply chain rule. So we multiply by derivative of cosine. Oops. Then what do we get? Derivative of cosine is negative sine x. So our final answer is negative sine x times square root of 1 plus cosine square x. So this right here is the derivative of this function. Compute the derivative of the function y equals integral from 0 to x tangent theta d theta minus integral pi over 4 to x tangent theta d theta. So here we have this entire thing is a function, but there's two functions that are subtracting each other, right? So what we need to do, we just need to find the derivative of this and minus derivative of this. Okay, so again, we're taking derivative of these functions. So I take the derivative of 0 to x tangent theta d theta. Let me actually write it all once together first. Minus pi over 4 x tangent theta d theta. But this is essentially the same thing as taking derivatives one at a time and subtract. Minus d dx pi over 4 x tangent theta d theta. So when we take the derivative with respect to x, we have to have a number. It doesn't have to be only 0, number, constant. And by the fundamental theorem, derivative of this is tangent x. So this variable goes here. Same here, derivative of this is constant, pi over 4 is number. So x goes here, tangent x. So we essentially have tangent x minus tangent x. So 0. So derivative of this function is 0. Compute the derivative dy dx of the function y equals definite integral from 0 to square root of x of 3t squared minus 4t plus 1 dt. So here this entire thing is an area function, right? Is an area, specifically is finding the area between x-axis and 3t squared minus 4t plus 1 curve from 0 to square root of x. So this entire thing is a function, and we're taking derivative of this function, this area function, d dx. So when we do that by the fundamental theorem, first we plug square root of x replaces the variable, right? So let's do that first. So we have 3 square root of x squared minus 4 square root of x plus 1. But then we have to multiply by derivative of square root of x by chain rule. So let's rewrite this. Well, we know this is 3x because square root of x and square means x. 4 square root of x plus 1 times square root of x. Let's write it as x to the half power to find the derivative. Maybe we can find on the side here. I get half x negative half by the power rule, which is same as 1 over 2 to the square root of x. So this we get 3x minus 4 square root of x plus 1 times 1 over 2 square root of x. So this right here is the derivative of this function. The velocity of an object is given vt equals t squared plus 1. How far does the object travel between 0 and 6? So remember, the definite integral can help us find the net change of a quantity. In this case, distance, how much it traveled. So if we take the definite integral of velocity, which is t squared plus 1, respect to time from 0 to 6, it will give us the distance it traveled, net change of distance. So let's take the antiderivative to evaluate the definite integral by the fundamental theorem of calculus. We get t cubed over 3 plus t. Evaluate this at 0 and 6. So I plug 6 first to t, and then I plug 0 and subtract from each other, right? But it has to be this order where we plug 6 first. So I have 6 cubed plus 3 plus 6. And it's good to have a parenthesis here as a habit. Minus plug 0 in. 0 cubed over 3 plus 0. So plug 6 here, and plug 0 and 0 here. So let's evaluate this. 6 cubed is 216 over 3 plus 6. Well, this is just 0, right? This is 0 over 3, 0. Adding 0, 0. So we have, what is that? We divide by that, we have 72 plus 6 gives us 78. So object travel 78 unit, whatever the unit is, 78 feet or 78 miles. The problem does not specify the unit, but we know they traveled 78, or that's the net change. The velocity of an object is given, vt equals negative 6t plus 15. How far does an object travel between t equals 0 and t equals 3? So here, taking definite integral between 0 and 3 of a velocity in respect to time will give us the distance it traveled. Because definite integral gives us the net change of velocity, negative 6t plus 15, respect to time. So let's take the antiderivative by the fundamental theorem calculus first to evaluate. So this is the antiderivative, which is negative 3t squared, I guess I should write here technically, plus 15t, 30. So first I'm plugging 3, and then I'm plugging 0. So let's do that in the next line. We have two things subtracting, right? Plug 3 first, negative 3 squared plus 15 times 3. So what I did here is I plugged this 3 right here, right, to this equation. And then I plug 0, negative 3, 0 squared plus 15, 0. So I plug 0 from the lower bound number. So let's simplify that. Here I get negative 3 times negative 3 times 9 is negative 27 plus 45 minus, this is 0, 0, 0, 0, so we minus 0, which gives us 18. So 18 is the amount of distance that an object traveled between 0 and 3. Again, it does not give us a specific unit. If it was feet per second, then it will be feet. If it was meters per hour, then it will be meter. Whatever the unit is, the object traveled 18 unit. And that's the net change between 0 and 3. Water is flowing out of a reservoir at 300 t squared liters per second for t between 0 and 5. How many liters are released in this period? So finding definite integral can give us the net change. So we want to find the net change between 0 and 5 seconds of the water flowing out at this rate, 300 t squared, with respect to time. So let's take the antiderivative, which is 300 t cubed over 3, evaluate 5 and 0. This can simplify to 100 t cubed, 5, and 0. So first we plug 5 in and subtract after we plug 0 in. Right? 100, 5 cubed. Let me do a big parenthesis. So what I did is I plug 5 here and subtract, plug 0, which is from the lower bound. 5 cubed is 125. This is subtracting 0. This 100 times 0 is 0. So we have 100, 125. What is that? 12,500. In this case, liters. So between 0 and 5 seconds, 12,500 liters of water were released during this period.